Should we discuss A together or the first part?
Uh,
The answer should be 2 over root 6, if I remember the problem correctly, for C, that constant C that's in the original linear combination of 3. And the idea is, in general, if we have some psi, this is supposed to be t equals 0. So at t equals 0, I know the shape of psi at t equals 0. I should be able to write that as a linear combination of states of definite energy. And the magnitude squared of each of these coefficients is the probability associated with a measurement of, somehow measuring the N, L, and M values. Then it's the probability that you find those values when you make a measurement. And so in this first case, psi at t equals 0 is going to be normalized if the sum, in other words, all these probabilities have to, their magnitude squareds have to add up to 1, the coefficients, right? So it's got to be true that the sum over all N, L, and M of the magnitude of C N, L, M squared equals 1. The interpretation of each one of them is a probability. And we're going to talk about what the probabilities associated with L and M represent. You know from the reading that they're associated with angular momentum, whereas the N is associated with an energy state, right? The energy only depends on N. But in any case, they've got to add to 1. Now, in this case, we don't have a sum of an infinite number of these. We've only got a sum of 3. So that means we only have 3 non-zero C's. Here they are, 1, 2, and 3. And they've got their magnitude squareds have to add up to 1. So when I take the magnitude squared of the first one, I get 1/6. Magnitude squared of the second constant in front of this is a 1/6. So the magnitude squared of the third one's got to be 4/6, right? Which means the coefficient C out in front has to be 2 over root 6. Okay. Now you also have to remember for B that energy is only associated with the N value, right? We don't care what L and M are for the purposes of energy. So take that into account when you're answering B. If you're stuck somewhere, feel free to ask a question. I keep bugging my oldest son who's in 7th grade, and they're learning about the quadratic formula and completing the square for the first time. And he just will never ask a question, even though he's struggling with homework. And of course, he always asks, when am I ever going to use this stuff?
Hey, I mean, he never knows when he might.
You never know. I mean, you just don't have the perspective as a seventh grader to know when you might use it.
Let's see.
Okay, so for, again, that constant C is 2 over root 6. And that gives us in B different probabilities for the energies E1, E2, and E3, because we see an n equals 1, n equals 2, and n equals 3 in there. Some of them might have been combined, and then we would have had to add the probabilities for that particular E. In this case, all 3 terms have different energies, where En is the minus 13.6 over EV over n squared. That formula, you know, where all those constants make up the minus 13.6 EV. Okay, and so this one's probability, maybe we should say prob of measuring E1 is just the square of the only coefficient that has an n equals 1 in it. So that's 1/6. Probability of E2, that's only the second one. So the square of its coefficient is 1/6. And that means that the probability of E3 is the square of the third coefficient, which is 4/6. And they all add up to 1 because those are the only 3 non-zero terms. So the probabilities of the energies have to all add to 1. Any questions on B? C, does your answer depend on the time you wait before measuring energy? Yi Chen shaking his head no. Why would that be? Yeah. Well, otherwise we wouldn't call these stationary states, right? And they are stationary states. Technically, you know, to put in the time dependence, we would say, oh, if I want psi of r, theta, phi, and t, what I do is write it as a linear combination. I shouldn't have erased what I wrote down. C, N, L, M. I need different C's for all of those. R, N, L, which is a function of R, and then Y, L, M, which is a function of theta and phi. I write that down for time t equals 0. And then to put in the time dependence, each one of these terms gets a factor e to the minus I E N T over h bar, our good old factor that we've had since the beginning of chapter 2. And you can think of this product here as being the expansion coefficients at a later time t, right? If we go at a later time t, this is the stuff that's multiplying it. So I might say, you know, the C, N, L, M are really time dependent. So they have some time dependence, but it's whatever it is at time t equals 0 times this. Now, when I take the magnitude squared of that product, this factor is going to go away. And so there's no time dependence to the probabilities. There's a time dependence to the coefficients themselves, but not to the probabilities when we take the magnitude squared. Okay, that's the answer to C. You have to write that out in a sentence or two as best you can. And then D, consider the state given by H psi. Is there any sense the outcome of a physical measurement, is it in any sense the outcome of a physical measurement of the energy on our state psi? This is sort of a confusingly worded question. I copied this from somebody else's worksheet, but I might have phrased it differently. But it's a good question. You might think, well, if I didn't understand quantum mechanics very well, I might say, well, if you want the outcome of measuring the energy, wouldn't you just apply the total energy operator to the state that you're in, and that would give you the outcome of that measurement? Superficially, it sounds like it might be true if you didn't think about it very carefully. Why? How can I show that that's not true? Of h hat, you mean? Yes, yes. So when we measure energy, we know we're going to get a definite energy state. And the state, I've erased my original state, but my original state was a sum of 3 terms, and each term corresponded to a different energy. When I measure energy, it's going to collapse to one of those states, definitely. And the other 2 probabilities will go to 0. It's going to discontinuously change. Now, if I just take that original state and apply the total energy operator to it, right? The total energy operator operating on the first term is just going to give E1 times the first term back again. And I'll get an E2 times the second term back again, and an E3 times the third term back again. So all 3 terms would remain if you applied H to it. So even though, to someone who doesn't think very deeply about the operators and what they do, it sounds like, oh, you make an energy measurement, that's applying the H operator to, no. That's not what we mean by it. There's a collapse that happens, and it's not the same as applying the total energy operator to it. Any questions on those? So again, try your best to write those answers up neatly. I am going to have you turn this in as part of your chapter 4 homework sometime later, and we will be working on it again in class. So to lessen your homework burden, we'll be doing some of that in class. I should also mention that I just noticed before class that last Friday or Thursday or something, I put up a chapter 4 part 1 homework assignment, and mistakenly it was actually I put the link to a chapter 4 part 3. So if anybody looked at it, it wouldn't make any sense in terms of what we had done so far. I've changed the link, so now it points to the correct homework assignment, which only the first 2 of those 4 problems are due on Thursday, I believe. Whatever the due date I had on there. There's stuff that we've already talked about, the hydrogen wave functions, I think. One of them is just like the problem we did in class. Let's look at the probability density as a function of R and as a function of theta. And can you tell me what N and L and M are? Or at least narrow it down to a small set of probabilities. That's kind of like what one of them is like. Okay, so take a look at those. They have to do with hydrogen, and we're going to be sort of moving on from specializing in terms of hydrogen, although this worksheet clearly keeps talking about the hydrogen wave functions in particular, the one we were just working on. All right, let me go into slide. Wait, that's not what I want to do. Let me set up my slideshow so it doesn't fill the whole screen. Let's go to Zoom, share screen, and let's go to slideshow mode. And we are going to be talking about angular momentum now. We're going to find out that we've already unwittingly found out a lot about angular momentum in the process of doing separation of variables for the hydrogen atom. If you read through all of 4.3, and please do, you're supposed to read it and post before today. I saw there was only one post in the website, which continues our tradition of non-participation, relatively speaking, of posting. So if you haven't done that, if you haven't read it, or if you didn't have time this weekend, just read it and post before Wednesday. I won't count it late, but after that, it's going to count as late so that we can, I like to at least look at your reading response questions. And if possible, address some of them in class. So just a reminder here that Planck's constant h, and therefore h bar, which is h over 2 pi, have dimensions of angular momentum. And so we're going to see that angular momentum in quantum mechanics is expressed in multiples of h. And we're going to be talking about orbital angular momentum for a while. We'll get to spin angular momentum later on, but orbital angular momentum corresponds to, in classical mechanics or in physics 210, to that r cross p. Remember, if you've got a particle that is moving with momentum p, let's just go back here for a second. So I've got a particle, you know, of mass m moving with momentum p. Then I've got some origin over here, and I can specify where that particle is with respect to the origin. And we denote that vector by r. And the angular momentum of this particle with respect to this origin is defined as r cross p. That's just what you learn in physics 210. Certainly you did something with it in classical mechanics. So we're going to be doing analogous stuff now. We didn't talk about it in one dimension because there's no sense of, you know, you need at least 2 dimensions to talk about angular momentum. So we didn't really have an opportunity to talk about it, but it's a classically conserved quantity, just like energy and momentum are frequently conserved, and you know, depending on what kind of system you're talking about, but it's going to play a central role in quantum mechanics. And we're going to define the angular momentum operator by analogy with the classical definition. So here we're just thinking about physics 210. Angular momentum of a particle is r cross p relative to an origin, right? Because r is where the particle is at that instant relative to the origin. If you work out this cross product, I don't know how you guys do cross products. A lot of times people write out a determinant, right, to figure out what the components are. That's how a lot of people learn it. Then you could figure out what the x and y and z components of this cross product are. In any case, they look like this. If you don't like doing the determinant, it's a little bit of a time waster sometimes. You can always figure out, here's how I remember it. I remember that somehow x, y, and z, I think of them in a cycle like this. So I'm going to start out with x and then go to y and then z. Or if I start with z, then I'm going to go to x and then y. So notice the pattern here. Lx is y times pz, right? If you remember, the cross product goes in terms of position and then momentum. It goes x, y, z for the first term. And then you've got to subtract these in the opposite order, right? Y pz minus z py. But the first one that appears is x, y, z. Or if I start with y, I go y, z, x, same cyclic ordering. And if I start with z, it goes z, x, y minus y, x. So that's a way to just remember what they are. If you can remember that cyclic ordering of x, y, z without, you know, spending the time of writing out that determinant and seeing what's in front of the y hat and all that kind of business. So we're going to define the, you know, since we want everything to work the same way, we've already carefully defined what the position and momentum operators are, right? Py is minus ih bar ddy and so on. So we want our angular momentum to be consistent with the definitions in classical mechanics. So we're just going to define our angular momentum operators to be exactly the same combination of operators as they were just for the dynamical variables over here. Okay, and they're all just, you know, if you can remember what Lx is, then you can, whoops, there we go. If you remember what Lx is, then by cyclic permutations, you can just immediately write down what Ly and Lz have to be. Okay, now we're going to start thinking about commutators between these angular momentum operators, and you know, it's going to take a while to kind of motivate why we want to know about the commutators, but we know commutators have been valuable for us already in this course. If we're going to take the commutator between, you know, sort of Lx and Ly, we're going to get things, you know, terms that will look like this, and you're going to actually figure out what Lx, the commutator between Lx and Ly is. It's going to reduce down to commutators that looks like this. And the question is this commutator zero or non-zero, or does it depend on the state that the particle is in? All right, let's see a vote on that. I'm not sure if you guys are ready or not. Gotta remind myself what my answer number is. It's about 50-50 between A's and B's in the class, so everybody's sure it's either 0 or non-zero. Can anybody make an argument for their case? Yeah, so Yichen says the momentum operator for Z does not kind of interact with Y. In other words, this is minus IH bar DDZ. And this operator, you know, in terms of the position representation, is just the variable Y, multiplication by Y. And you can move that Y in and out from in front of to behind that derivative with respect to Z all you want, because you know, Y is a constant with respect to partial derivatives with respect to Z. So it's actually 0 in this case. And we're going to find that there's a lot of zeros that sort of simplify our life when we take commutators between these things. So let's try, this is not on the worksheet we were just doing, but for Alvis and Gracie, I think this was posted on Friday's date. There's a worksheet that has at the top angular momentum. And we're just going to do problem number 1, which is to compute the commutator LZ, LX. That's the single sheet one that I handed out a bit ago. Well, yeah, I got to substitute the mess that's in the box there for LZ and LX, right? I've got what they sort of reduced down to, and then I've got to try to simplify that mess. So spend a minute trying to simplify it and see if you can use the fact that anytime you have a commutator between a derivative of one type and a variable of another type, you know, like x and ddy, that commutator is automatically 0. But if you have a commutator between a y and a ddy, or a y and a py, that's definitely not going to be 0. So we're going to use the fact that the commutator between y hat and py hat, somebody remind me what that commutator is, or x hat and px hat, it's the same thing. Yeah, it's IH bar. You encounter it in the opposite order, then it's minus IH bar, but in this ordering where the position goes first and the momentum goes second, it's just IH bar. I'll also note that at some point you get really tired of putting hats on everything. So even though technically all these should have hats on it, it's such a pain to put a hat on every operator when you have 10 of them appear, you know, or how many do I have here? 8 of them appearing just in one line. So sometimes I just say, I'm going to drop the hats for a second, just for the sake of my own sanity, even though I know these are operators. So, maybe it's worth just for starting carefully with this. To simplify this, I need to kind of distribute over the minus signs here, right? I've got a sum here and a sum over here. And you ought to at least think about, is there some way I can distribute it or kind of FOIL this out, if you like, right? Just multiply different ways. So we're encountering something like this. If I have a commutator between these, by definition, this is again, I'm dropping the hats here for my own sanity, minus C times A plus B. And in this case, notice that if I just put the AC stuff first, I got to keep all these are operators, so I got to keep them in the same order. So this is AC minus CA plus BC minus CB. So that's equal to the commutator of A and C plus the commutator of B with C. And so anytime you have a sum or a difference, you can kind of distribute the commutator symbol over that if you get the idea of what I mean by distribute. So in this case, the first thing I can do is just say, well, this is xpy comma ypz. That's the first times the first. And then I can do the outer, right? Now I want to erase all this stuff to give me more room. That's first, then outer. When I'm doing this, I always got to keep the operators in the same order that they appear. Minus, from that minus sign, xpy comma zpy. And now let's do inner. Minus ypx comma ypz. And now let's do the last terms. I get minus times minus is plus ypx zpy. Again, I've got to remember those are operators. I'm being lazy and leaving off the operator symbols or the hats just because they're so annoying when there's so many of them. And then the question is, how do I think about these? Are any of these four 0? The two middle terms are 0. In other words, well, let's see. If you had the number 2 sitting here, you would happily factor the 2 outside of the commutator, right? Because it appears in both terms, and you could factor out in front of the whole thing. And the constant 2 certainly moves through any kind of operator. It's the same way with x or with z, because in this case, I'm only talking about derivatives with respect to y, and the x's and z's can move through. So I might, if you like, one step of simplification is I can factor out the x and the z, and then I'm talking about the commutator between py and itself, and every operator commutes with itself. So that term is definitely 0. Similar kind of thing over here. I've got px and pz, which certainly commute with each other, partial derivatives of different types, right? ddx and ddz can always move right through each other. It's ddx that can't move through an x. There you have to be careful. But in this case, the y doesn't interact with either of those, so I might just write this as y squared times the commutator of px and pz, which certainly is 0. Good, so the middle two are 0. Why isn't this one 0? Yeah, because I've got a y and a py. I have to be a little bit careful with this one. And similarly over here, I've got a y and a py. The z and the px don't really care so much, so let's just work on those. Here, the y and the py I have to keep inside, but the x can move anywhere, and the ddz in here can move anywhere. So I can write this as x times pz, again, those are operators, times py comma y. And then that one over there is, what can I factor out in front? a px and a z times the commutator of y and py. Again, I'm keeping them in the same order they appear in the commutator. Okay, and we just decided that this thing was IH bar. And this is just them in the reverse order. So this is a minus IH bar, right? And now I can factor out the I and the H bar, right? I, H bar, and what I'm left with is a ZPX minus XPZ. Right, after I factor out the I, H bar, I have a ZPX minus XPZ. It doesn't matter the order I write those two in, but when I write them in this particular way, this is the same thing as the commutator. I'm sorry, this is the definition of what? Let's go back to our definitions of angular momentum. ZPX minus XPZ is the same thing as LY. So I can write this thing in parentheses here as LY hat. Okay, not the most elegant demonstration of this, but certainly every step was pretty straightforward. So let's erase the mess and write down the punchline here. Okay, let me show this in the video. We just found out that this was IH bar LY hat. And since these are sort of have a cyclical symmetry to them, right? LZ is to LX in terms of LY, as you know, LX is to LY in terms of LZ. So, you know, the same exact proofs go through in exactly the same way, telling us that LX, LY is IH bar LZ. Hats on everything there. Something went wrong here. LX, LY is IH bar LZ. We've got XY, now we need a YZ. LY, LZ is IH bar LX. Put hats on everything if you like. So those are our commutation relations between all possible combinations of these. And you might say, well, you know, big whoop, who cares? But we're going to make good use of these later on. And in fact, we'll see that they really are crucial, knowing what the commutation relationships are, because as you know, these are angular momentum operators. We're going to encounter something about spin angular momentum, which isn't really specified by a wave function in three-dimensional space. And so there we're going to have to cling very closely to these commutation relationships. Okay, so we expanded out that commutator. We found the middle two terms were 0, and we wrote the resulting operator in terms of one of the angular momentum component operators. And so there's our three commutation relations. Okay, in the notes I say, well, who cares? I guess there's two reasons that we should care. The first is that we're going to use these commutation relations much the same way as we did in the harmonic oscillator. We're going to define some raising and lowering operators or ladder operators that are going to allow us to very easily figure out what the kinds of definite angular momentum states that we can find are shortly. But the second reason is that when we encounter spin angular momentum, we won't have the option of doing differential equations, solving partial differential equations and all that kind of stuff, because there is no function of position that's going to represent the spin state of an electron, for example. Okay, well, they don't commute with each other. And that means there's a non-trivial kind of generalized uncertainty principle that you can write down. For example, one combination would be the uncertainty in Lx times the uncertainty in Ly is greater than or equal to h bar over 2 times the uncertainty in Lz. And you might stare at this and get a little bit worried or confused that, you know, we think about what we found out with x and px, right? We said sigma x times sigma px is greater than or equal to h bar over 2. That means that if the uncertainty in x gets really small, the uncertainty in px has to go off to infinity. And so, at least if you stare at this for a second, you might say, well, wait a minute. That means if I know Lx really well, if I know the x component of angular momentum, I have to be infinitely uncertain about Ly, or at least that would be the superficial interpretation. And that would be true if this other thing weren't here. But actually, we're going to find out that every time, if you're in a state of definite Lx, for example, so the uncertainty in Lx is 0, it's always going to be true that this expectation value is 0 in here. And if this expectation value is 0, the whole right-hand side is 0. And that means that, lost control of my pointer. That means that just because sigma Lx is 0 doesn't mean that sigma Ly has to be infinite. That would be true if the right-hand side were some finite number. If sigma Lx is 0, sigma Ly can still be perfectly finite, and the product will still be 0, and that's satisfied as long as the expectation value of Lz is 0. So we're going to find that that's always true. If you're in a definite definite angular momentum state, then the expectation value of either one of the other components of angular momentum is 0, even though there's still uncertainty, right? Just because the average is 0 doesn't mean there's not some spread in it. Okay, but the important point is here, if they don't commute, we've already discussed that there's no complete set of simultaneous eigenfunctions for any pair of these three operators. Certainly not for all three, but not even for 2 of them. So if we're in a state of definite Lx, if it doesn't commute with Ly, then that's definitely not a state of definite Ly. If you know Lx, you can't know Ly definitely. And same thing for all the pairs we can get. But we can do something that's not quite as good as knowing all 3 of these together. We can define another operator, which is the square of the orbital angular momentum, which is defined to be just the sum of the squares of those individual operators. And it's just a matter of tedious calculation to check that if you do the commutator of that squared angular momentum operator with any of the 3 components, it's 0. Okay, so what that means is L squared and Lz are compatible operators. So are L squared and Ly. So I can find a set of eigenfunctions or eigenstates or eigenvectors, which are simultaneously eigenfunctions of the square of the total angular momentum and the z component of the angular momentum. And that's going to be important for us. So we can't know Lx and Ly at the same time, but we can know Lz and L squared, or Lx and L squared. We can know one of those pairs, and we'll always stick with Lz for, just historical reasons. People like z better than x or y for some reason. Okay, so that means, again, we can find a complete set of simultaneous eigenstates for L squared and Lz. And so here we're going to imagine, okay, let's find this f. Maybe this f is it's going to be a function of spatial variables, so a function of r, theta, and phi, right? And we can find such a state such that L squared operating in that state is a constant times that state. Let's call the L squared eigenvalue lambda, and let's call the Lz eigenvalue mu, and it's the same state. And there should be a complete set of those states. I'm just writing down the conditions for one of them. In the notes, I think I put a subscript B on these, but there's no good reason for that. So if you're following along with the notes, you can just scratch out the B's there. There shouldn't be a B in there. Okay, now we could solve for these eigenfunctions the good old-fashioned way, right? this is really a differential operator, right? Because there's, I can put in the ddy there and the ddx there and figure out what L squared is, and that involves differential operators. This is a partial differential equation, and this is a partial differential equation. We could solve those and find the solutions as a function of r, theta, and phi, but we're going to do things in an easier way. And again, just like before, you kind of have to accept a definition, and we'll see the utility of the definition later on. We're going to define raising and lowering operators. And this isn't a single subscript plus minus. It means we're defining two operators. There's an L plus operator. And so the upper subscript here goes with the upper sign here. L plus is defined as Lx plus ILy, and L minus is defined as Lx minus ILy. So we're making two separate definitions, just being lazy and writing them in one statement. Okay, so let's go to that same one-page worksheet and do problem 2, which is to work out two commutators that are shown on the slide there. And they're actually not nearly as much work as the one we did before, but find the commutator of LZ with L plus or L minus, and find the commutator of L squared with L plus and L minus. So we'll find that L squared commutes with it, but LZ does not commute with L plus, nor does it commute with L minus. I'll arrow back to our commutation relations at the bottom there. Okay, I've written some stuff on the board, which was just the start of this problem. I'm first going to do it in terms of L plus only, and then we'll put in the minus case later. Commutator of LZ and L plus, I just put the definition of L plus. It's Lx plus ILy. And then I distribute in the way we talked about. Any constants can be pulled out in front of the commutator. And then I've got to remember these commutators, right? We said Lx commutator Ly is I times the Lz operator, right? So sorry, IH bar times Lz. So Lz times Lx, again, going in cyclic form. Zx, then we get Ly after that, right? And what goes out in front is an IH bar. Similarly, Zy, Zxy, yes, thank you. And then LZ, LY, well, the one we had was in the cyclic form where we had Y, Z, and then we got X. So that would be an I, H bar, LX. Since these are in the reverse order, we get a minus I, H bar, LX. I think that's right. And so I've got I times I is -1, which cancels the -1. So I get H bar times, H bar times LX, I believe, plus ILY. And that again is the definition of L plus. Right, so I get an H bar L plus. Now let's just figure out what happens if I would have put an L minus in here. I would have put an L minus in there. We should have had a subtraction there. That's the definition of L minus. You subtract instead of adding. That would have given me a minus here. And that would have actually been a minus I times a minus I, which would then be a -1. And I would have, in this case, subtracted. Let's see. If I get this minus, that would change this term to minus. And so that would change the, well, let me do it one step at a time. That would have changed the LX term to negative, right? Let's factor out the minus sign from the whole thing, minus H bar times LX minus ILY. And that LX minus ILY is by definition L minus. So I think all that is summarized by, in the case where we had the upper subscript, we got a plus sign here. In the case where we had the lower subscript, we get a minus sign there, and we get a minus sign down there. Does that agree with my notes? Yeah. Okay, and so questions on that? Just formal manipulation, but good practice with commutators. I know this isn't stuff you've been doing since high school, right? And then the second one we're supposed to calculate is the commutator of L squared with L plus or minus. And what is that one? That one's even easier. Based on what we said that we could check. Where is it? You can check here that the commutator of L squared with LX is 0. And the commutator of L squared with LY is 0. And this is defined in terms of LX and LY, right? It's LX plus or minus ILY. So those commutators are both going to give 0. So this one's 0. Again, who cares? Well, we're going to show why right now, why we should care as I go and check the time. I think we have time for a 5-minute proof here of why we should care about these commutators. Okay, here's the central claim of the important part of this, and we're going to do some algebra to prove it. So I put the commutators we just figured out on the worksheet up here in the corner. And the claim is that if we call, there's some eigenfunction of L squared and LZ. So we're going to say f is an eigenfunction of L squared with eigenvalue lambda, and f is also an eigenvalue of LZ with eigenvalue mu. I should have just written this out in symbols rather than in words like that. I'm not sure why I wrote it out in words. It just seems to make it more opaque. We're saying that L squared on f equals lambda times f, and LZ on f is mu times f. So if this is the case, then L plus or minus on f, okay, so if this is the case, we're supposed to be proving, or this is the claim, then L squared applied to L plus or minus acting on F is the same number lambda acting on L plus or minus on F. And I better leave myself a little bit more room for this one. LZ acting on L plus or minus acting on F is mu plus or minus H bar times L plus or minus acting on F. What's the importance of this before we go into the proof? The importance is that if you can, just like we did with the harmonic oscillator algebraic solution, if you can find a state which is a simultaneous eigenstate of both these operators, then by using L plus or minus, we can find a different eigenstate. It can't be the same eigenstate. It can't be a multiple of it because it has a different LZ eigenvalue. And so it's truly a linearly independent state. And we're going to use this to form a ladder of linearly independent states of definite L squared and LZ. All right, here's the proof, in as much as we have time. Let's just compute what L squared is acting on L plus or minus F. And let's compute what LZ acting on L plus or minus F is. This is the easy one. Look, those two operators commute, so I can switch their order willy-nilly. That's what commuting means. So I can write them in the different order. And we already said L squared operating on F is by definition lambda times F. And that lambda can be pulled out in front. So if we take this new combination or this new state, it has the same eigenvalue for L squared as the original one without the L plus or minus acting on it. The interesting one is LZ. When we take LZ operating on this, I can't just willy-nilly switch those two operators. Why would I want to switch those two operators? Well, because when LZ operates on F, it just gives me mu times F. And I want to use that fact. And in order to do that, I have to get the LZ next to the F. But I can't just switch them because they don't commute, right? They have a non-zero commutation relation. Here's how we proceed. We force the commutator to appear. We say, here's the original term we had, LZ acting on L plus or minus F. What I'm going to do is subtract those two operators in the reverse order, acting on F, but then I'll add them back in. And if I subtract it and add the same term, I haven't done anything, right? But this thing that appears right here, this difference is actually the commutator of those two operators. And when that commutator acts on F, LZ, L plus minus, that commutator is plus or minus H bar times L plus or minus acting on F again. So these two terms here simplify down to plus or minus H bar, L plus or minus acting on F. And what do you say about this third term here? How can I write it as something times L plus or minus F? Well, it's mu because the LZ, LZ acting on F is by definition mu times F. We're assuming it has eigenvalue mu. It's an eigenstate. So this gives a mu coming out, and the mu it's just a number. The eigenvalue is a number. It can go back out in front of the L plus or minus F. Now combine these two terms together, we get mu plus or minus H bar times L plus or minus on F. And that proves the theorem, which, judging by your faces, is not too exciting. But what it's telling us is that we have a whole ladder of states. We start out with, if we can find one state, we can find a whole bunch of states. And they all have the same value of L squared, but they have different values of LZ. That's called the ladder associated with a particular L squared value. And we'll keep working on that on Wednesday. I put the first two homework problems due in Thursday's class, I think, on the worksheet that's now, or sorry, the homework sheet that is corrected on the website. Take a look at those. They have to do with the hydrogen atom stuff nothing to do with angular momentum, so you're ready to do them now. Please, 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 last call for those Dirac notation and the last homework kind of stuff. If you don't get it to me today, bring it to me in my office tomorrow. Because I just want to close the door on that and start grading them. So if you don't have time to do it today, bring it at the latest by tomorrow and come by to see me.